Hi, everyone. I'm Andrey. I'm the founder of dstack, which is an open source tool for orchestrating GPU workloads across any clouds. And today I'll be talking about open source LLMs and different nuances of how you can leverage them for production. We'll talk about major open source models, some economical aspects of using them, how to optimize it. We'll mention some frameworks also. And of course, we'll discuss questions. So please think of questions, what you'd like me to cover also. In the end, we'll have some time for that. A quick one before I continue. This is going to be an introductory level presentation, and disclaimer here that if you are already deploying open source models for production, well, I cannot really promise that you'll learn a lot. However, if you are only interested in adoption and you had some experience with LLMs, but now looking into basically using one of the open source models, this talk is certainly for you. But again, we'll see how it goes, and if we have enough time, we'll get deeper into this topic. All right. First question to ask in regard to open source LLMs is why at all to consider open source LLMs. I assume most of you already have some experience with LLMs in general, large language models, and services like OpenAI, Anthropic, and others. And those services are quite convenient to use. And the question is why open source LLMs and what is the difference and all. And I would say there are at least four major reasons to use open source LLMs. And first one is control. So what is control? Think of these services like OpenAI and Anthropic and others. Those services operate models that you don't own. You basically use them as a service, and you don't control the behavior of the model. So basically, you depend on third-party service, and it can happen that this service may change the behavior of the model at any time, and you have no direct control of that. And imagine that your business depends on the behavior of the model. The behavior may change at any time, and you risk basically to lose control over your business. So that's one thing, and that's why open source LLMs are a game changer here. And you might also hear the word open weights LLMs. So it's not exactly open source LLMs, but it's open weights LLMs. It means that the weights of the models are open, means that you can own them and you can have entire control over them. The next important reason for using open source LLMs is customization. Think of open weights LLMs means that you can not only use them, for example, for inference, but you can also build on top of these LLMs. And also think of the entire ecosystem and community. So, for example, if one company open sources an LLM, it means that on one hand, you can use these weights for deployment, then you can fine-tune this model, then you can also follow the architecture of the model and try to use it for training another model. And by sharing weights with the community, you allow the entire community to build on top of your model and customize this model for very specific use cases. And this is a very powerful thing, which we'll talk about in more detail today. Third aspect is, of course, privacy, very important topic. And all of the companies, I guess, have certain view on privacy and how important it is. Basically, by using a service such as OpenAI or similar one, there are some privacy implications. It means your company might not be open to sharing data with third-party services. Your company might be interested in, for example, hosting the inference in your own service at all. So open source LLMs is a great way to control privacy. And finally, costs. Think of using open LLM and similar proprietary services. They are typically priced per usage. This means you are paying per request, or to be more precise, per token. And most of the time, the more tokens you generate, well, the more it costs, and the costs actually rise linearly, which might be very expensive, especially if your usage is very your usage is very high. If you are using open source LLMs, there are ways to significantly reduce the cost and have the growth of the costs not linear but logarithmic. And of course, you can reduce costs significantly by using a smaller model and fine-tuning it. On one hand, you are using the smaller model and pay less money. On the other hand, you can fine-tune the model to increase the quality for very specific task you need your LLM for. Right. A few words about major open source releases, and by no chance I can cover all of the major releases. Open source LLMs announced pretty much if not every day, but certainly every week. And there are so many different models that are worth looking at. But those three on the slides, I'd like to mention specifically. First is, of course, Llama 2. It is probably one of their first high quality and fully open source models, which you can use commercially without restrictions. This model is released by Meta in partnership with Microsoft, and it's offered in 3 different sizes. You see 7B, 13B, and 70B. B means billion of parameters. It is a measure of how large the model is. And this is also a measure how good the quality of the model is. And of course, the larger the model, the more expensive it is to use, but we'll also mention in more detail what is the implication on cost here. Llama 2 is offered in 2 flavors. One is a base model. And base model means that it is not, well, it is a base one, means you can fine tune it for different kind of tasks. It's very versatile. And the other one is chat model, or also known as instruction model. Means that it was fine-tuned on instruction tasks and chat conversations. And this is very useful if you'd like your model to follow instructions. That's why it's offered in 2 variants. Then another very important model is Code Llama, which is basically a fine-tuned version of Llama 2, also by Meta, also offered in 3 different sizes. But what is interesting about this model is that think of an LLM that can generate text, natural language text, but compare now it to a model that can generate code that can be automatically executed. So in this case, you not only can create content, but you can also automate a lot of different tasks. For example, think of generating SQL queries, and then by this automating the access to your data on your behalf, or generating JSON requests, which may enable an LLM to make API requests to third-party services on your behalf. So this is a quite powerful thing, and it opens many new use cases for LLMs. And finally, Mistral was released not long ago. Mistral is a very small model. It's only offered at 7 billion parameter size, but I basically have to update this slide because Mistral just recently released a larger model called Mixtral, which has a significantly more complex architecture and much larger size. But if we have enough time, we'll talk about it. But basically, that makes Mistral the third most worth attention open source LLM. Right. Just to give you a feeling of how open source LLMs compare to proprietary services, this is the original benchmark data from the Llama 2 model, where on the left-hand side you see all kind of benchmarks. First one, for example, MMLU, massive multi-language understanding benchmark. It basically tells how an LLM performs across many different tasks. And you see that Llama 2 comes quite close to GPT 3.5, but it significantly lags behind GPT-4. And there is no surprise, of course, because Llama 2 has the size of 70 billion parameters, while GPT-4 is more than twice larger, and GPT-4 is 10 times larger than GPT 3.5. But what was mentioning here is basically open source LLMs come close to the quality of proprietary models. Right. Here's another one with Mistral, the smallest model. Why this model is cool? Because this is the most performing small model. Basically, it performs better than any other model of the same size. And its quality on certain tasks match the quality of, for example, Llama 13 billion parameters. And as you may also see here, that for some tasks, it comes really close also to the quality of larger models, like, for example, 34 billion parameters. In the end of their presentation, I'll probably also share the slides so you can watch these charts in more detail, and also look for the links and references to find the sources for all this benchmark data. Right. So let's talk about fine-tuning. So why open source models are great is primarily because you can fine-tune them. Why would you fine-tune an open source model? Two reasons. Number one is this is how you make your model perform very specific task. Imagine that you'd like to generate very specific kind of code. Then you would take a base open source model and you would fine-tune it on your specific data set to get the quality that you couldn't get, for example, with other models on your particular task. And the other reason is to reduce the cost. And how is it possible? By leveraging a smaller model and fine-tuning this smaller model on your specific data set, you make it possible to use a smaller and cheaper model and at the same time have the quality of a larger model. So here's the study by Snowflake, where they took Llama of different sizes and they fine-tuned it on data set prepared for generating SQL queries. And what they figured out is that by fine-tuning the smallest Llama 2, they actually achieved the same quality of much larger models like Llama 70 billion parameters. And also, interestingly enough, it came very close to the quality of GPT-4 for generating SQL queries. Right. Here's another list of benchmarks that compare to other models: Wizard Coder, 34 billion parameters, and Find. And those two models are built by some companies. and they were shared as open source models. And they are interesting because at the time when they were released, they actually claimed that they bet their GPT-4 quality for generating code, which basically proves that it is possible to fine-tune an open source model on such a task as code generation and have a quality that comes really close to GPT-4. However, then GPT-4 updated their model and it still ranked as their #1, but still those models are really great at quality for generating code. Right. A few words about cost aspect of using open source LLMs. Here's a screenshot of an application that basically measures how much memory you would need to deploy your model or to fine-tune your model. This application is shared on Hugging Face Spaces, and later you'll probably get the link to try it out yourself. But it, for example, here shows how much memory you would need for using Llama to 70 billion parameter model. So every model is a set of weights, and these weights is a set of float point numbers, basically. And the way you, in order to run inference or training of this model, you have to load these weights into memory, basically GPU. And for that, you need a lot of memory. So here, if you take the original full precision weights of the model, it would take 256 gigabytes just to run inference. Basically, it just tells that it's not possible to fit it into one GPU in order to run inference. And we are talking about Llama 2, largest model. But there are techniques that allow us to significantly drop the requirements, and we'll mention that. And for training, typically you would need 4 times more memory than for inference. Again, this depends on many factors, including, like, for example, what optimizer you're using. But let's now switch to, let's also talk about the cost aspect here. This is a study by Hugging Face done together with AWS. So what they did, they took Llama 2 of all 3 different sizes, and then they used instances, cloud instances from AWS to run inference. And then they measured latency and cost for generating 1 token and for generating million of tokens. And you see here that for the smallest model, you would need a still quite expensive instance, and for generating 1 million of tokens, you would need $32, which is quite expensive. And if you are taking the largest model here, again, we're talking about full precision without any optimization techniques, then generating 1 million of tokens would cost you more than $400, which is insanely too much. And basically, you would need the largest instance AWS has. It's an instance that offers 8 GPUs, 8100 each with 80 gigabytes. Right. So, and that brings us to their first optimization technique, which you can use to significantly drop their requirements for the memory. And this technique is called quantization. As I said, an LLM is stored as a set of weights, float point numbers. And because this is a very large set, you need a lot of memory to fit all these weights, all of these float point numbers into memory. And this technique allows us to lower the precision of every parameter, for example, from float point 32 or float point 16 to, let's say, integer 8 or integer 4. Basically, we are replacing a higher precision with a lower precision data type. And the whole point here is not only to reduce the amount of memory needed for that, but also to ensure that the quality of the model doesn't drop. Because we reduce the precision, the quality might drop as well. But this technique is quite powerful, and a lot of studies show that that the drop in the quality is not significant. But again, it raises the lower precision you use, the higher the quality drop is. For example, if we get back to this application that shows how much memory we need for inference and for training, we see, for example, and can compare if we are using Llama to 70 billion parameters and we use quantization, and for example, instead of 32 float points 32, we are using, let's say, int4, then we just need 32 gigabytes of memory. Means that we can fit it into one GPU easily. And also for training, but for training, you see that we still need 4 times more GPU, and that's why typically for training you would still need well, more than one GPU. Let's also get back to this study by Hugging Face and AWS. This one shows if you are using quantization, then how the cost per token and cost per 1 million of tokens changes. So basically now if we take the largest Llama 2 model, 70 billion parameters, and apply quantization, we don't need the largest AWS instance anymore. We are fine with a bit smaller instance. And then the price for generating 1 million of tokens drops to $60. Which is quite good. Right. Speaking of fine-tuning, there's another very powerful technique called low-rank adaptation, or LoRa for shorter. Again, when we talk about an LLM, it is a set of weights, and the main issue here is to fit all of these weights into memory. And for training or fine-tuning, we need, well, almost 4 times more memory than compared to inference. So that's a bottleneck, and often you don't have that much resources, but you still would like to train or fine-tune model. And this is when this technique comes really handy. So what we do here is instead of fitting the whole weights of the model into memory, we split, or we basically take the weights and take a subset of these weights, which we then call an adapter. And instead of loading all the weights into the memory, we only load in this adapter subset of weights and fine-tune it. And once the fine-tuning is finished, then we merge this adapter weights with the rest of the model. This works because we select only a subset of parameters of the model, and quite often, in order to train or fine-tune model for a very specific task, you don't have to train the entire model. You don't have to use all of the parameters. Sometimes it is just enough to use a subset of these parameters, and that's why this LoRa works. And this allows us significantly drop the requirements for the memory. Here's some benchmark data for fine-tuning and also inference. Now for Falcon, 180 billion parameters. It's the largest open source model, by the way. So we see that if we fine-tuning this model without any optimization techniques, we would need well, 5 terabytes of GPU memory, which is just insane. 8 machines, each with 8 GPUs, well, one of the most expensive GPUs. However, if we apply quantization and then LoRa on top, you see that it's just enough to use 160 gigabytes. Basically, we're almost like 25 times drop in the memory requirements, and it's just enough to use 2 GPUs to train that very, very large model. Right. Speaking of their accuracy and their quality drop when using these techniques, this is the study by Anyscale, and they took basically, again, Llama 2 of different sizes, and then they fine-tune it on 3 different tasks. First one is functional representation, which is just another name for extraction of structured data. Second is code generation, SQL generation, and third one is solving math problems. And they fine-tuned Llama model with and without these optimization techniques, and then they compared the quality. And what they figured out is that even by fine-tuning the smallest Llama 2 model, it is possible to achieve the quality of much larger models and even GPT-4, and even exceed the quality of GPT-4 significantly with these optimization techniques for specific tasks, such as, for example, extraction of structured data and code generation, which is just another way to say that this optimization techniques is super powerful, and for a variety of tasks, it allows you to achieve much better quality than, for example, OpenAI or similar services. If you prepare a right data set and use this technique. So even with spending a little money, you can get quite good quality. Right. So speaking about fine-tuning, how fine-tuning actually and how training works. The most basic way to fine-tune a model is through supervised fine-tuning. And think of this as the following. When an LLM is being trained, first it's trained on low quality data, but this is the most expensive step. You basically take the entire internet, and then you basically fine-tune your model, so the model starts to learn how to generate code based on this low quality data. You don't need any human in the loop. You just need a lot of GPU, a lot of compute, and you need to train that model for a very long time until this model learns from this low quality data. However, then if you like your model to generate some high quality results, then you would have to fine tune this model on high quality data. And this is what's called supervised fine tuning. You basically have to prepare a smaller but higher quality data set and continue the training pretty much same way for not long time. And by doing this, you get significant improvement in the quality of your model. This is called supervised fine-tuning, and there are libraries for doing this, so it's pretty easy to use today. For example, if you are using Hugging Face Transformers library, then you can also use another library from Hugging Face called SFT. You just need to prepare a data set in the same format that model supports. And then you can apply these optimization techniques through this library. With just a few lines of code, you can run fine-tuning of your model. This is very easy to do. All you need to do is to prepare this data set. Another more powerful way to fine-tune a model is through, for example, reinforcement learning, also known as reinforcement learning from human feedback. If you think of fine-tuning, again, supervised fine-tuning, it's when you tell your model which result is good. So basically, you just feed a lot of examples and then tell this example is good, that example is good, and that trains the model to generate good examples, but it doesn't align the model in terms of what is bad example. So it still can generate a lot of bad examples. And in order to avoid that, you would have to not only tell which example is good, but also which examples are bad. And this is when you need this reinforcement learning. How it is different from supervised learning. In a way, it's pretty similar. You also prepare a data set, same format, but on top of that, you add labels. For example, like good or bad. So you basically have to annotate each piece of data set with these labels. It could be categories, or it could be just a number from 0 to 10, how good this example piece is. And then you would have to run this training in slightly different way. In the case of reinforcement learning with human feedback, you would have to first train what is called reward model using these labels, and only then basically run the final training where this reward model is used. And there are libraries. Again, Hugging Face offers this TRL library for that, which allows you to quite easily run it, even though it's more compute intensive and time intensive. But it's still not very hard to do. You would just need to annotate your data. Also important to mention another relatively new method called DPO, direct preference optimization, which can be an alternative to reinforcement learning. It works, it uses a different algorithm, which doesn't require you to train that intermediate model. And that's because of that, it's less time needed for training, and it's less compute intensive. But it still would require you to prepare these data sets in the same format as if you would use RLHF. And there is some data that shows that by using this method, you can achieve either same or even better quality than with using RLHF. For example, Hugging Face used these methods to train Zephyr. It is a fine-tuned version of Mistral, and this experiment shows basically that you can reach Llama to quality or even exceed this quality, even though the largest Llama was trained using RLHF. So, which is just another way to say that it's quite powerful technique, and it's totally recommended as an alternative to RLHF. Right. Again, to conclude the presentation and maybe proceed to answering questions, there are several things which I'm not going into, but I'd like to mention. And first one is known as serving multiple LoRa's. As I mentioned in the previous slides, there is such a technique as LoRa, low rank adaptation, which allows you to take a subset of all the weights and only use this subset for training. And the same technique can be used also for inference. And when it is useful, imagine that you'd like to run inference for 1,000 of LLMs. Every LLM needs a lot of memory. So, for example, if one LLM requires one GPU for running 1,000 of LLMs, you would need 1,000 of GPUs, which is just insane and just almost impossible. So what LoRa allows to do is, if all of these 1,000 LLMs are fine-tuned versions of one model, then you would be able to load the weights of that original model, and then only load the fine-tuned adapter versions of that model. And by doing that, you would be able to load pretty much all of these models into few GPUs and run inference. So this is why this technique is super powerful. And this technique allows you to basically run inference for using a lot, like much fewer resources in infrastructure resources. Then the other one is speculative decoding. Well, when you run inference, you would basically every invocation of the LLM, it is the bottleneck, and it takes a lot of time. And there's a technique known as speculative decoding, which allows you to drop that time needed for inference by, instead of invoking one large model, delegating this invocation to several models, and then calculating the chances how the result is good. And then if we speculate that the quality of the result is good enough, we don't have to invoke a larger model. And by doing this, we significantly drop the time needed for inference, and we basically reduce the latency. This is the way how you optimize inference time. Finally, another thing that I would recommend you take a look at is synthetic data sets. So as I mentioned, when you fine-tune models, one of their most challenging parts for you is preparing a data set. It takes human labor to collect and curate and validate the data sets. And this is something where you could actually use other LLMs, involve other LLMs in helping you. So basically, you can use LLMs for generating your data sets, or for validating your data sets, or for annotating your data sets. So this is a quite powerful technique, and you can use LLMs for all of these things. And there's some body of research that shows that it actually works. So I totally recommend to take a look at it. So having said that, I'd like to conclude and switch to the questions. Right, let me see. So how does a larger number of parameters drive higher cost? Is it RAM, CPU, or GPU? Thank you for the question. So first of all, like I said, in order to run inference or training, you would need to load all these weights into memory. So basically, there is a linear relationship between number of parameters and amount of memory which you need. The less parameters the model has, the less amount of memory you need to run inference or training. The more memory your GPU has, the more expensive this GPU is. Or the more memory you need, probably the more expensive GPUs you would need. So basically, that's how it works. Speaking of RAM, CPU, and GPU, all what matters is their latency. You can use any memory, but of course, if you compare, for example, RAM and disk, then RAM would be a lot faster. However, if you compare GPU and RAM, GPU would be a lot faster. And this is why GPUs are used for generative AI most of the time, because they are a lot faster. There are certain projects that help you leverage CPU. For example, the most famous, of course, Llama CPP, which I recommend you to check out, which allows you also to leverage RAM for running inference and probably for training as well. But that not sure. That this one not sure. So the general answer is yes, it is possible to use CPU and even disk instead of GPU, but GPU would be a lot faster. Hope that helps. But please comment if there's other question in like about memory. So another one is could you elaborate on the licensing of the major OS models, open source models? Heard that Llama is free until you reach certain scale. Thanks. Yes. When we talk about Llama, I said that it's free for commercial use. However, if you look at the original license, you'll see a clause saying that once you reach certain number of users, and you do deploy this model, then you would need Meta's approval or Meta's confirmation that you can use it. That's exactly true. But this number is pretty high, so you would have these problems only if your usage is really high. But anyway, of course, it's worth checking up the license and making sure that you can use it. Again, there are ways of probably if you have so many users, I guess it'd still be possible to contact Meta and then get that approval. And now there are other, of course, open source models that don't have this clause. So it's only about Llama 2. Hope that helps. Which framework should I use to deploy an open source LLM for production? There are quite a few very cool frameworks. One is text generation inference. It is a toolkit by Hugging Face. It's basically a Docker image, which you can give just any model name from Hugging Face Hub and additional parameters, and it will basically serve this model quite conveniently. And I would even say that that's one of the most convenient ways to serve model. There is one maybe note here that even though it's open source framework, there is a clause that if you would like to run inference as a service, then you would need, again, just as like in Meta's case, Hugging Face approval for that. So which might complicate if your intention is to host models as a service. Another one is VLLM. Which is entirely open source, and there are no any strings attached, and it's pretty convenient. It's super fast. Just like text generation inference, there are many optimization techniques already built in, and both projects are being maintained. So can totally recommend of using them. Then finally, there is TensorRT. It is a framework. Not entirely, not for serving, but it's a framework that is quite helpful if you'd like to serve a model. It allows you to compile any given model into a specific for specific infrastructure to make sure that the latency is really low. This framework is by NVIDIA, and it can be used together with other frameworks, like, for example, Triton. It is a framework, again, by NVIDIA for serving. I guess these three are most interesting, but then there are, of course, many others, many cool libraries. Yep. All right. Is there a source you recommend for keeping up on current LLM foundational models and their benchmarks? Well, speaking of benchmarks and models, I guess there is this OpenLLM leadership board where you can see how open source LLMs compare in terms of benchmark. And as soon as in terms of benchmarks, and as soon as there's a new model that performs really well, you'll see that this model popping up in this leaderboard. And then, of course, Twitter is a nice way to follow what's going on, even though it's quite overwhelming. And there's no easy way to keep track of things without spending quite a lot of time. My rule of thumb is typically keep track of major releases, and then taking a look at the papers of these major releases, because it's often helpful not only to know about a new release, but also learn about, okay, so what makes this new model different, what approach was used, what data set was used, or whether it was synthetic data or not, what is the license, and so on and so forth. And then what are their implications of fine-tuning this model? Right. Need to know how to put an LLM after tuning to production. The general workflow is the following. All models have different architecture, but not all of them are different. Some models share architecture, and there are certain similarities, and there are frameworks which serve as adapters for these models. For example, if you take transformer, this is the library by Hugging Face, and it allows you to run inference, also to run training of a model that uses this transformer architecture, and it tries to incorporate basically the support for specific models that have this architecture. And you can look at the list of the issues on GitHub to see, okay, so for example, if Mistral is out, then Hugging Face team makes sure that transformer libraries support this model, and so on and so forth. So basically, it's a community thing. But once the framework has adopted it, then you can use this framework for working with this model. And typically, if you fine-tune a model, you would use also a framework for serving it. And it's pretty straightforward, basically. For example, if you take Llama 2, you fine-tune it using this SFT or TRL library, and then you would deploy this model using text generation inference I mentioned, or VLLM I mentioned. So it is quite straightforward. But unless you have more specific question, let me know. Open source used to mean source code is shared. Are open source LLMs sharing the source code they use for training the foundational model, or does it mean the FM is public use, not the source code? Exactly, that's what I mentioned. Most of the time when you hear there's an open source model, it means that this is an open weights model. And again, based on my observation, most models don't share the code used for training, but there are, of course, models that do that. Which is quite cool. But in general, it's better to use the term open weights model. Means that there's not always code for training, there is no public data set, and so on. Right. If a foundational model already a known number of parameters, I assume created through training, does that mean people only load and call their model? Do they load the model on their own machines, or do they also call this model hosted on the managed service? It doesn't really matter. It can be done anyway. You can load this fine-tuned model locally and run inference. You can deploy this model of yours to your servers, or you can deploy it to any cloud infrastructure, or you can load it into one of the managed services. So having said that, this is an additional slide. As I mentioned, I'm a core contributor to dstack, which is an open source tool for orchestrating GPU workloads. With this, for example, you can use all of this open source framework I mentioned: VLLM, text generation, TRL, SFT, and all others, to either train, fine-tune model, or deploy this model anywhere you want in the cloud. So basically, it's compatible with any open source frameworks, and it is compatible with any cloud provider. For example, if you're using AWS or Lambda, or I don't know, TensorDoc or VastAI, you would be able to define your training or deployment configuration with dstack and run it easily on the cloud of your choice. Basically, it's your call to choose how you want to deploy or train your model. There are ways to do it all different ways. Does memory have to be GPU, RAM? Can you use CPU? Yeah, I mentioned that already earlier. When you say training, do you mean training from nothing, or do you mean extending the main using something like fine-tuning? I use it interchangeably, and there are people that actually, well, argue that fine-tuning is the same as training. But technically speaking, it could be different. But I personally use it interchangeably. Basically, you just continue training your model slightly different way, or maybe exactly same way. It would be useful to define what are embeddings, tokens, and parameters. Yep. If you have reference architecture for LLMs that shows a system model with things like Hugging Face, long chain versioning, that would be really useful. Yeah, totally agree. Often it would be cool to basically see, okay, so what tools can I use for training? What tools can I use for serving? What tools can I use for managing data set? That's true. And I wish there was a simple diagram, but maybe something to create. So if somebody wants to do that, that's a cool thing to do. Does anyone use cloud-specific ACICs for LLM inference, like AWS inference or GCP TPU? I assume the question is about very specific acceleration chips. Well, I'm not an expert here, but there are quite a few reports showing that, of course, NVIDIA GPUs is the leader in the market, and most actually using GPUs. However, of course, there are quite many companies that use specific types of chips, and of course, there's a growing demand for alternatives because there's a high need for GPUs, and there's only one company that builds them. So totally, there's a need for alternatives, and there are alternatives actually, but GPUs are still most used. How is the model deployed in production web development? Can you describe the architecture if it wouldn't take much time? Very briefly speaking, typically you first deploy your LLM endpoint. And for example, the most common format is the same as OpenAI, as long as we're talking about chat-like model. And then on top of that, you are using thing called RAG, or retrieval augmented generation, things like LangChain, Llama index, and similar, to, on top of your endpoint, build a pipeline that invokes that LLM, incorporating the data and managing the prompt the right way. This is how it is typically done. And then you expose this RAG endpoint again as an RAG pipeline as an endpoint. And in the end, your application invokes that RAG endpoint, and your RAG endpoint uses vector database through LangChain, Llama index, and other techniques, and then invokes the LLM. So basically, RAG is the answer to the question. Do you need GPUs for efficient inference, or can you use CPUs? Yeah, I guess I mentioned that. Llama CPP is a popular project for using CPU. And it is possible, even though GPUs, of course, much faster. But yes, basically it is possible. And well, quite a few people say that that LLMs soon will be possible to run entirely on like local devices, even though of course we still gonna deploy LLMs anyway. What about controlling things like temperature, hallucination, offensiveness in production using open source LLMs? It's pretty same when you deploy a model. Frameworks that allow you to do that allow you to control this, and well, every library that offers you to run inference allows you to configure that. And for example, if you are using the endpoint format similar to OpenAI, there's a way to control that as well, same way. And then there's RAG, where you can use certain prompt engineering techniques to manage other stuff. Right. Wondering how long does it take to fine-tune some of the foundational models and how much computer resources are needed? I'm not a big expert here, and I would totally recommend you to yeah, basically read some of the blog posts by experts, and there are quite a few. For example, if you look for um, for open source models, basically on, for example, Hugging Face, you'll find a lot of people that share models, and often they blog about how they fine tune it all. But fine tuning is much easier than training the base model. So basically, I mean, if training a base model would require you months, and like, I mean, again, this depends very much on how you do it, what GPU you use, and one company might use, I don't know, train a model for 1 month and then use a lot of GPUs. Another company would find a bit more or significantly more efficient way of doing this and leveraging significantly less, fewer GPUs and spending significantly less time. So in the end, it's typically expensive, it's typically long, but if you do it the right way and if you prepare the right data at all, you can reduce the time and money like really significantly. And it could be just hours of fine tuning. Again, it depends entirely on the task. If for example, you fine tune for a very specific task, it could be a small data set and you can fine tune just a couple of hours and then still get pretty good quality. And it could cost you, I don't know, $10, $5. Right. What is the physical form of an LLM? Is it a binary object that is executable? Is it a model stored in format like Unix? So originally, a model is a set of weights, basically parameters and activation. Data. It's basically numbers like float point, or if it's quantized, it's integer numbers. And there's a way to compile it. For example, TensorRT allows you to compile this to binary code, but that's not always required, but it is possible. Yep. Right. So let me know if we still have time. Otherwise, I can continue. Can you talk about distributed? Yep.
Andrew, feel free to continue for the next 5 minutes. And then if there are any more questions that are left, we can redirect them to our Discord channel where you can engage in a real-time conversation with all the participants. We've shared the link to the Discord in the chat. So feel free to, answer the questions that you can in the next 5 minutes.
All right, thanks a lot. Yeah, then let me take another 5 minutes for that. Can you talk about distributed training? And can this be used along with techniques like LoRa, RLHF, and all? Again, this one I'm not a big expert here in distributed training, but certainly these techniques are possible to use. Like for example, RLHF for sure it is possible to use with distributed training. I guess that's doable. And then I guess LoRa is possible as well. In the end, we are talking about LoRa is just a way to take a subset of your model and then fine tuning this model. And in that sense, it's just another model. And of course, we can train any model using distributed way. In the end, what really matters is how easy it is to use. Like for example, PyTorch gives you a very low level abstractions, and it has certain abstractions for distributed training, like data parallelization and others. But if you are using a higher level library, then you would basically have to rely on that library. So in the end, it depends on the library. And then how easy it is depends a lot on the library, but it's still pain in the ass, if I can say so. It's not that straightforward when it comes to distributed training, but it gets much easier with every month, I would say. So totally recommend googling some blogs about distributed training that show how to do that easily. In the end, there is also a problem of setting up the cluster right way and making sure that if something fails, the thing, and it's quite a lot of engineering work. So it's still not a piece of cake. For hobby projects, if you don't have access to local powerful GPUs, do you rely on cloud services to fine tune and use LLMs? So the answer is yes. Even if you are GPU poor, like people say these days, it is possible to leverage open source LLMs. However, I would say, of course, it depends on what exactly you do. So if you are doing something very simple, there's a very high chance that somebody else follow this route and there's a way to do it. So if you are fine-tuning the model on very specific tasks, probably it's very easy to do. Also, RAG is something where you can increase the quality of your model very significantly, and it's relatively easy to do, and you don't need a lot of resources for that. So I certainly recommend to check this out. And then in the end, you first have to start with the problem. And typically, again, based on my little experience, you typically start with a problem, then you build a very quick prototype using OpenLLM, sorry, not OpenLLM, but OpenAI. And then you see, okay, so how do we achieve the same quality or close quality using an open source LLM? Do we take an existing model? Do we fine tune it? Do we fine tune embeddings? Do we, just fine tune the model to run RAG and all? That's how it works, I guess. Word model can be run on edge devices like Raspberry Pi. I'm not an expert. Unfortunately, can't really tell what Raspberry Pi can do. But yeah, maybe there are some interesting blogs about that. But Llama CPP, I would certainly look at Llama CPP first for this. What models can run on the edge? Okay, that was the same question. This is GPU RAM. I guess it was following up on some other question. What about OpenVINO toolkit powered by Intel? Using that, we can able to optimize the large model and we can run inference, right? Not an expert in OpenVINO toolkit, but I guess yes. The question is like, does it support the model you want to use? Does it provide all other things that you can use with other libraries? So basically, I would just recommend you comparing OpenVINO toolkit to other libraries, and then you'll know whether you can use it or not. So basically, can't really say more precisely. And yeah, let me take two more questions and then we'll wrap up. do you have some resources where I can read and learn in more detail about how to make my own application using open source LLMs and fine tuning to my custom use cases? That's a good one. I don't think there is, well, there are quite a few blog posts that tell you, okay, I don't know any machine learning. I just took an open source LLM and in a few days learned how to fine tune it to solve my specific problem. So there are blog posts like that. However, I would not, hope that there is one blog post, like 5-minute blog post that would show you how to solve your problem. So first start with the problem, and then probably if you have a specific problem, there are a lot of people that already doing this. So it depends on the problem, basically. Yeah, sorry for not being able to give a more precise answer here. But the general answer is yes, there are many resources. First, start with the problem, understand what you want to achieve, build a quick prototype OpenAI, and then basically look at fine-tuning RAG pipeline and fine-tuning the model. And the final one. So how can we realize that we need fine-tuning or we need just prompt engineering? Very easy. You prompt engineer, and then if the quality is good, then you don't need fine-tuning. But hope this helps, but it's maybe it's too simplified, but that's how I would approach it. Awesome. Yeah, sorry that I didn't have enough time to answer all the other questions, and I was quite amazed by the number of questions, and I'm looking to answer them through Discord later. All right, so I guess
That's great.
yeah, we can
Andrew, I
wrap
hope you
up.
had a good time engaging with the live audience.
Amazing actually audience, and I really love the questions at all. And like I said, I'm surprised by many questions, and I really hope that my answers helped at least some people. I will share the slides and also the list of links where you can see the references and more detailed benchmark data. And also check out the dstack Discord channel, and I invite everyone to this server, and I'll be very happy to answer more questions. And if you need help with open source models or need some directions, I would be happy to share it. So please come to the Discord channel, and also check out the GitHub repo of dstack.